So this video is looking at measures of position, which answers the question, where does each score or a particular score fit relative to the whole picture, whether that's the whole sample or the whole population. So like with our mean, median, mode for measuring central tendency and standard deviation, variance, and range for measuring variance, we have more than one way to measure the position. So one way to measure position is something called Zed Scores, and this is kind of unique to statistics. It does get used a lot. We'll use it a little bit here in Chapter 3, and then we'll start using it big time in Chapter 6 onwards. So this is something that's going to come back. With these Zed Scores, our formula has two different symbols, but it's actually the same formula. Right, so our symbols here are sample symbols, our symbols here are population symbols, but they're both take the particular score you're concerned about, your x, minus your mean, and divide that difference by your standard deviation. Typically, we round our Z-scores to 2 decimal places, partially because your typical tables are shown to 2 decimal places, including the tables that we use in this course. So we've got an example here. We have Fred achieving 83% on his exam. The class average was 68%. The standard deviation was 12.7. What is his Z-score? And by the way, I do pronounce Z-score the Canadian way, not Z-score like an American. So we start with our formula. And we plug in our values. So 83% is going to be our x, our average is 68%, and our standard deviation is 12.7%. So we plug that in and calculate the difference. And then divide by 12.7, and we get an answer of 1.18. So what does this tell us? Well, if we look at that value, that tells us that the score that Fred achieved is 1.18 standard deviations above the mean. Give me a second here. And to have that all in blank. And we know it's above, not below the mean, because it's a positive Z-score. So Z-scores can be positive or they could be negative. With the standard deviation, we mentioned that ordinary or usual values fall within 2 standard deviations. Well, the Z-score is measuring how many standard deviations we are away. So ordinary or usual Z-scores are going to fall between plus and minus 2. So one of the things Z-scores are handy to look at is if we have things on 2 different scales. So for instance, here we have things done where one we have the mean of 100, the other we have the mean of 40. They're just being done with completely different scales. And so if we want to compare what's better, a score of 130 on test A or a score of 52 on test B, we have to do a calculation to get them to be in the same scale. So one scale we can use is those Z-scores. So if we calculate the Z-scores here to compare these two, right, so the first one we're going to be taking 130 on test A, so we would go, sorry, (130 minus 100 divided by 15). On test B, we're looking at a score of 52 minus our mean divided by our standard deviation. Should probably put in a subscript here. So that's test A Word really wants to capitalize that, but we don't want it to. And that's ZB. So our first one works out to 2.00. Again, I encourage you to calculate that one and make sure you can figure out where that number came from. Our second score works out to 2.40. So if we just looked at the 130 and the 52 without taking them back to these Z-scores, all we could really tell is that they're above average. They're both above average. But when we compare the Z-scores, we can see that, the 52 on test B is 2.4 standard deviations. Not only is it higher than the 2 of test A, it's an unusually high value, right? It's outside of that plus or minus 2. So therefore, we can decide that 52 on test B indicates a higher IQ than 130 on test A. So that's Z-scores in a nutshell. Another group of things that we can look at are percentiles, quartiles, and deciles. And percentiles, quartiles, and deciles are all looking at ways of dividing data into groups and saying which group a particular score fits in. Now when we talk about these, we're always talking the first is the lowest. So if someone's in the 92nd percentile, they have a higher score than someone in the 89th percentile. Or if we're comparing quartile, someone in the third quartile is higher than someone in the first quartile. So percentiles we usually symbolize with a capital P and a subscript, whichever percentile we're talking about. And they're often obtained through graphs. A typical place you may have seen this is if you have seen the graphs for children's growth charts. They'll show what percentile, the growth charts will show the 50th percentile, the 75th percentile, and the 90th percentile, and the 20th percentile, sorry, 25th, and the 10th percentile on the lower side. So many different calculations are used. Some are slightly different from each other. Excel actually has multiple percentile calculations. They have what's called the inclusive one and the exclusive one. The value that your textbook uses is this formula that we have shown here. This is one that typically we're looking at with large data sets. So you are more likely to be doing this one on Excel. So I'm just going to leave you with the definition here, and we'll do some Excel examples in class. Quartiles and deciles are basically, again, different computer programs use slightly different results, but basically what we're doing is dividing the data into however many pieces we're talking about. So quartiles, you may guess, quarter is 4, we're dividing it into 4 pieces. Deciles, we're dividing it into 10. So the quartiles, one quick method, if we're looking at a small data set, is to literally divide it in half and then divide our halves in half. In other words, find our median and find our other 2 medians. So looking at this set of 20 data points, if we were to do that, I'm actually going to physically use the pen tool and show dividing this into pieces. So if we do that, right, we have half our data points there, and then 1, 2, 3, 4, 5, half our data points there. Sorry, a quarter of our data points and a quarter of our data points, right? So we cut our halves in halves. So if we look at that, that would be our 4 quartiles. So when we're calculating that, that first line I drew, we would say is Q2. It's the second quartile, or the median. The line I drew here is showing where our Q1 is, and that's 15.5, right, because it's halfway between 15 and 16, just like this one, 19 and 20, halfway between was 19.5. I just realized these thicknesses had units. Back in example 1, we said they were millimeters, so we better say millimeters here as well. And that third one, halfway between 22 and 24, gives us 23 millimeters. Now sometimes with quartiles you will also see Q0 and Q4. That's our boundaries. No values are below Q0. So if we look, typically we'll go just below our first category. Sorry, gotta scroll up here. So our Q0 in this case we would say is 11.5 millimeters. There's no values below that. And it gives us some wiggle room for measurement measurement error. Sorry, having trouble speaking. Measurement error, right? So that's why we go a little below 12. Likewise, our Q4, we would go a little above 29. To 29.5. So we have all those values shown. Again, different textbooks will do this slightly differently. Excel will also do this slightly differently, but that's the quickest manual way to do it, is just to literally cut it into quarters. Okay, so there's our measures of position for an individual data point.